This video is about some important thermodynamic concept called enthalpy. So enthalpy is given the symbol H, and this video is all about unpacking a little bit about what that means. So let's go back and start again with the first law that we've been talking about. So the first law says that the total internal energy change, delta E, in our system, that it can only change through two ways: heat going in or out, and work being done on or by the system. So in our last video, we learned about something called pressure volume work. So if we have a constant external pressure, then we can take this equation and rewrite it, substituting what we know for the work done on or by the system. So delta E, and I'm going to drop my cis subscripts, but you'll remember that everything that I'm talking about is specific to the system. So delta E is equal to Q minus P external, so that's that constant external pressure, times the change in volume. So this right here is just my formula for PV work. Now what I'm going to do is take this formula and solve it for Q. So this now tells me any heat that goes into or out of the system is equal to the change in the internal energy. So that's one way that we can change the heat of the system, is because the internal energy of that system has changed. But it might also change because there's been some work done. So we're going to add that in as well. So we're going to add plus P external dV to both sides of this equation. And this is what we come up with. Now over here on this side of the equation, we have energy, we have pressure, we have volume. All of those things are state functions. They only depend on the state of the system at the current time, not how you got there. So this collection of state functions, we're going to call it a new thing. We're going to call it enthalpy. So this is equal to delta H, where H is this new collection of state functions that we call enthalpy. So we can write a definition. What is H? How does it relate to these other things? H is equal to energy plus pressure times volume. So that's enthalpy. Now, this doesn't help us understand enthalpy a whole lot, but this equation is kind of the important one up here. And what's important about it is that anytime your system changes its enthalpy, so just like it can change its pressure, change its volume, change its energy, it can change its enthalpy. And when it does that at constant pressure, and so that's very important to remember, this condition applies. So if this condition does not apply, this stuff isn't as useful. But anyway, at constant pressure, the enthalpy change is just equal to the amount of heat that goes into or out of the system. So I'm going to put a little subscript P next to that Q to remind us that this is at constant pressure. Sometimes enthalpy is called the heat content, because it tells you the potential of your system to undergo some change and release a certain amount of heat, release or absorb a certain amount of heat. And so delta H is sometimes called the heat content because it relates to how much heat can go into or out of something at constant pressure. Another way of thinking about what enthalpy is, I had a professor that once talked about enthalpy as being existence energy. It's supposed to be quotes there. So enthalpy is a lot like energy. In fact, it is equal to energy plus some other stuff, and it's going to have the same units that energy does: joules or calories or liter atmospheres, whatever energy unit you like. So it's called existence energy because if we think of something that exists in this world, let's scroll down here and think about a person. So here's a person, right? So for the person to exist, all of the molecules and atoms and electrons and things that make them up, well, that gives rise to the internal energy of the person. But if a person is to exist in the real world, then that person also has to create space. So that means they have to push the rest of the surroundings out to create space for themselves to exist. So you have to consider all the energies of their particles moving around and interacting, their potential energies, And you also have to add in this bit, the plus P times V. So that's the work done to push the rest of the surroundings out so that an object can exist in the world. And so anytime an object changes, it may change its internal energy, but it also might change the amount of space it takes up. And that will change its existence energy, this thing that we call enthalpy. So we use enthalpy in chemistry a lot because very many things that we study take place, let's say, in open beakers. So beakers that are open to the atmosphere. So there's some reaction that's taking place inside this beaker. So I'm going to abbreviate that RXN. And on pushing down on this beaker on the surface of this water right here is atmospheric pressure. All those molecules that are piled up in the atmosphere above our heads, well, they're pushing down with a certain amount of force. Gravity's pulling them down, and so that's going to give rise to a certain force on the top of the liquid. We call that the external pressure. And over the course that you might do an experiment, that atmospheric pressure is pretty much constant. So a lot of the reactions that we do in chemistry are under constant pressure. If that's true, then this applies, that delta H is just equal to the amount of heat that comes into or out of our reaction. And that's really what we're interested in this chapter, is thinking about heat that comes in or out of a reaction. And that's going to be equal then to this change in enthalpy. So we've already talked a little bit about how if heat comes out of a reaction, so if it generates heat, if the system, right here our reaction, loses heat to the surroundings, then that Q is going to make this reaction what we call exothermic. So exo means coming out, and so the heat is coming out. So if we go back here and look at our delta H then, and think about our sign convention, remember, when Q is going out of our system, we give it a negative sign. That's our convention. So when the system is losing energy to the surroundings, it's going out, we get a negative sign. So whenever delta H is less than 0 or negative, that's another way of saying negative, right? That means that we have an exothermic process. If delta H is positive, that looks like delta A. Let's try that again. If delta H is positive, right, greater than 0, that means positive, then we're going to call the process endothermic because energy goes into the system. It's absorbing that heat energy because the energy is going into the system. Let's think about this in the context of phase changes. So let's say in this beaker I have a liquid. And so if I want to convert that liquid into a gas, so I'm going to draw a little arrow up here, and then here's a big cloud of gas. So we've gone from liquid to gas. Then that process is called vaporization. And I know to make that happen, right, I have to add energy. So this is called the so this is an endothermic process, right, because I'm having to add heat. Now if this process takes place at constant pressure, then that heat is going to be equal to the enthalpy change. And since this process is called vaporization, we're going to call that the delta H of vaporization. Delta H vap. That's equal to the amount of heat that you have to put in to vaporize a substance. And so normally we will express this in the amount of heat energy that you have to put in to vaporize, say, 1 mole of substance. So delta H vaporization for water, for example, is equal to 40.67 kilojoules per mole. So this is the amount of heat energy that you have to put in if you want to convert 1 mole of liquid water into 1 mole of water vapor. So for example, if we have, let's say, 9 grams of water, and we want to know how much energy would it take to vaporize that water, how much heat energy would you have to put in? How many joules worth of heat energy, or how many kilojoules? Well, we can figure that out by using this number. So this is how much heat energy we have to put in to vaporize 1 mole. So that's the enthalpy change. So we're going to go uphill in enthalpy. We're adding energy in as heat. We're adding in 40.67. So just to emphasize that, I'm going to put a plus sign here to make us think that this is endothermic. Remember, when delta H is positive, it's endothermic. So the energy is going uphill by 40.67 kilojoules per mole. So do I have a mole? No, I have 9 grams. So how many moles is that? Well, we can do that conversion, right? So we're going to say 9 grams, that's supposed to be a decimal point right there, of water. We know that there's 1 mole. And off the periodic table, we can add up 16 plus 2 hydrogens. That gives us 18 grams of water. And so that works out to be about half a mole. So if it takes 40.67 kilojoules to vaporize 1 mole, if we only have half a mole, well, it's going to take less energy. And we can calculate how much less. So all we have to do now is take this 0.5 moles and multiply it by 40.67 kilojoules per mole of water. The mole unit will cancel out, and 0.5 times 40.67. Pull out our calculator here and get a good number. 0.5 times 40.67 is 20.34, and that unit is in kilojoules. So 20.34, I know that doesn't look so much like a 3 because my pen keeps doing this funny thing. Anyway, 20.34 kilojoules of heat energy. So that's how much heat energy you have to put in to vaporize half a mole or 9 grams of water.